This is the sample test number for chapter 3, and the first one says find the critical points. We do that by setting the derivative equal to 0. So first we'll find the derivative, and so the 3 times this will cancel the 3, so we get 2x squared. 2 comes down, cancels the 2, so we get plus 3x. And then derivative of minus 5x is minus 5. And so if I set 2x squared plus 3x minus 5 equal to 0, it factors to 2x plus 5 and x minus 1. So x will equal negative 5 halves, or x will equal 1. Then if I get the rest of the points, go to my calculator and go to the y equals, clear, and type in the original equation, 2x to the third divided by 3 plus 3x squared divided by 2 minus 5x. The second table, and put in negative 5 divided by 2, and I get 11.4458. So the points, because I said find the critical points, so their coordinates, so minus 5 halves and 11.458. And then if I put in 1, I get 1 comma negative 2.833. Okay? And so these are either max or mins, and so it says use the second derivative test. So I'm going to take the second derivative. F double prime of x would be 4x plus 3. And so I want to check at minus 5 halves. So this would be, if I put in minus f double prime of minus 5 halves into this is 4 times negative 5 over 2 plus 3, and that's 2, that's minus 10 plus 3, that's negative 7, so it's concaved down, making this place a maximum. We can kind of anticipate that already because that's higher than this one, and this was a cubic, and so this is probably a minimum, but to do the second derivative test to show that, we put 1 into the second derivative, which would be 4 times 1 plus 3, which is 7, which means it's positive, it's concaved up, and makes this a min. If it's concaved up, that means it's a minimum. So that's the idea of problem number 1. Problem number 2. Find the absolute max and min of this. So I'm going to go to my calculator, start off right away, and type in 4 sine, well, let's clear this, 4 sine, we're going to do pi x divided by 2, and close the sign, minus x. And second table, and I got to put in minus 1. I get 3. So f of -1 is 3, and f of 1 is, oh, it's -3, excuse me. And then I put in f of 1, and I get 3. And now I've got to take and find the critical places. So I've got to take the derivative. And that would be the derivative of the inside is pi over 2 times 4. Derivative of the bigger picture is cosine pi x over 2 minus the derivative of x is -1. And then I got to set this equal to 0. So the 4 and the 2 cancel, so I get 2 pi cosine pi x over 2 equals 1 by setting it to 0, move the 1 to the other side. So then I divide by 2 pi on both sides. So I got to get the cosine equal to this, so I take the cosine inverse of both sides, and I'll get pi over 2 times x equals the cosine inverse of 1 over 2 pi. Now, 1 divided by 2 pi is that. So I'm taking the cosine inverse of that. But just to be clear, on the unit circle, we're talking about 0.15, which is in here close. There's a couple places where the cosine is 0.15. Up here and also down there. So when I do cosine inverse of that answer, I get 1.41 radians, but it's also negative 1.41 radians, and multiples of 2 pi from there. Now, it's not these that have to be between -1 and 1, it's x. So we've got to take these two answers, pi over 2 times x has to equal either plus or minus 1.41. So I have to multiply both sides by 2 over pi, and to get rid of that, and so x is going to be 1.41 times 2 divided by pi, and I get 0.898. And that would be plus or minus. And both of those are between -1 and 1. So I have to look at those places and see whether I have higher or lower values. So I have to do f of 0.898 and f prime of 0.898 approximately. And so I get these approximate max or mins. Let's see what we get here. So I go to to table and put in negative 0.898, and I get on the negative one, I get negative 3.051, which is a little bit lower than this. So here's the max, the global max. And if I put in the 0.898, the positive, I get 3.051. 5, 1, that should be our global. Oh, this is the global min, sorry. And this is the global max. Okay, that one's a little bit messy. I'll try not to make as messy a problem on the test. Find the inflection points for this. So just so I know what I'm looking at, I'm going to type this in. It's x times e to the x graph. So it looks like it curves down, then it curves up. So there's an inflection point somewhere here on the negative side. And I get inflection points by setting the second derivative equal to 0. So I got to find the first derivative. And this is a product, so I take a prime b plus b prime a. Derivative of x is 1 times e to the x plus derivative of e to the x is e to the x times x. Factor out the e to the x times 1 plus x. And there's the first derivative, and so it looks like I would have a maximum in at x equal minus 1. That looks reasonable. Let's go zoom forward, see it a little closer. Looks like we got a min at minus 1. But that's not what I need to find. So the second derivative would be, and I could do this and do the product rule, but I can also just do it right here. The derivative of 1 times e to the x is e to the x, and the derivative of x e to the x is what we just did on this first one. So it'd be all of this again plus e to the x using the chain rule, the product rule, plus x e to the x. So now I have e to the x in this, and if I factor it out, I get 1 plus 1 plus x. So 2 plus x. So this is equal to 0 at x equal negative 2. And so at negative 2, and I said find the points, so I have to find the y value. So I'm going to go to the second table and plug in negative 2, and it's negative 0.271. So that's the point, that's my inflection point. And I can see it in my graph right there. It looks like it's curving down, and then it curves up, changes at minus 2. Okay, page 2. All right, so now these are first derivatives, and I'm supposed to decide whether it's A, B, C, D, or F on each of these graphs. This is the first derivative. So this whole graph is above the x-axis, so it's always positive. And if the first derivative is positive, I have a positive slope. And that's true for all of these. So all of these, the original function, have to be increasing because they have the slope is positive. Not the slope of this graph, but the value of the slope, since these are the first derivatives, are all positive. Every one of these graphs have to be increasing. F has to be increasing because the slope is positive. And the slope of this is always negative, and the second derivative, therefore, is negative. Which means this one has, the original function has to be concave down since it's negative. And so an increasing and concave down is letter D. So this is going to be, F is going to be a letter D graph. This one, it's positive slope and then it's negative slope. So it's concave up because the second derivative is positive, and then the second derivative is negative, so then it's concave down. So always positive slope, concave up, and then concave down, but increasing the whole time. Concave up, then down. So that's letter E. This one has always got a positive slope, so it's always concave up and increasing, which is letter C. All right. Now this problem, 5, I'm telling you whether the slope is negative or positive, and I'm telling you whether it's concaved up or down. So it's concaved up, concaved up, concaved up, concaved up, concaved down. It's increasing, decreasing, increasing, decreasing, increasing, increasing. And this is intentionally supposed to happen right here. So it's saying up to -3, it's got to be decreasing. So if I were to make a graph down here, where this is 0, this is -3, this is 3, and this is 5, and I'm lining things up, I have to make a graph that's got a negative slope and concave up. So negative slope and concaved up, and then now it's got a positive slope and concaved up. So it must hit a minimum here. Now it's concaved up and increasing. It doesn't have to be concaved up much, but increasing. Then it has to have a negative slope, so it must have reached a top, but it's got to be concaved up and then still concaved up. So that means there's a cusp right here, because the only way I can be concaved up and then concaved up and go from a positive slope to a negative slope is to make a sharp turn, a cusp. If I round it, I'd have some concave down, and there was no concave down. Still concaved up, decreasing, and then increasing, so that's sort of like what we had before. Plus minus to plus plus. Minus plus to plus plus, minus plus to plus plus. And so I have this a minimum again, and then here I have to keep positive slope but change my concavity. So now I'm concave down. Okay, so there's an inflection point there, no inflection point, no inflection point, but a non-differentiable place right there. That's the idea of problem number 5. Number 6. Got a rectangular sheet of metal, so I'm going to draw my picture, rectangle. And I'm going to make an open top box by cutting squares out of the corners. Does this sound like a familiar problem to you, I hope? And then folding it up. And the sheet was 3 feet by 6 feet. And determine the dimension of the box at maximum volume. So the volume would be, well, I got to decide where to put X. I'll put the size of the squares I'm cutting out. I guess I could call X. I could call this X. I could call this X. But I think best here just to call the squares I'm cutting out X by X. So this length of the box, remember the volume of a box is length times width times height. So my length would be 6 is all the way. If I'm cutting off X on this side and X on this side, this would be 6 minus 2X. And then this way it would be 3 minus 2X. And when I fold this up, the height of the box will be that x. So there's the length, the width, and the height. If I multiply this together, I get, because this, if I had to take the derivative of this, I'd have a product rule. So I'm going to take the multiply this together. I'm going to get 18 minus 12x minus 6x plus 4x squared, and I got to take each one of these times x. So I've got 18x minus 18x times x squared plus 4x squared. So now, a third, 4x to the third. So v prime would be the derivative of this. I'm going to put them in power, descending power. So the derivative of this would be 12x squared. Derivative of this would be minus 36x. And the derivative of that is plus 18. Got to set that equal to 0. So I'd have 12x squared minus 36x plus 18 equals 0. I think I could factor out 6 at least, and so I'd have 2x squared minus 6x plus 3 equals 0. And I don't believe that factors, so then I would have to go to the quadratic formula. And so setting this equal to 0, x would be equal to the opposite of b plus or minus the square root of b squared minus 4 times 2, which is 8 times 3, 24, all over 2a. 36 minus 24 is 12. So I got 6 plus or minus the square root of 12 divided by 4. I could simplify that, but what do I need? So it says, find the dimensions of the box that would have maximum volume. So the box, the base of the box would be, the length would be 6. And if I do the minus, which we've got to, first of all, make sure these are reasonable answers here. So let's check that. 6 plus the square root of 12 divided by 4 is 2.36. Oh. Could I cut 2.36 and 2.36 out of the 3? Nope. So that answer is not a plausible answer. So I'd go 6 minus the square root of 12 divided by 4, and I get 0.634. So the only answer out of here that I can use is x equal 0.634. So my length will be 6 minus 2 of these, which is 1.27 minus 1.27, which, and my width would be 3 minus 1.27, and my height would be 0.634, the x value. So there's my height. In feet, this would be 1.73, if I'm doing my mental math correct, and this would be 4.73. So there's my length, my width, and my height. And they'd be in feet. Number 7. 500 meters of fencing to be used to make equivalent rectangles. Determine the dimensions of the corrals. And I forgot to put in here for maximum area. So I want to maximize the area in this. Now I could put X here and Y here. I could put X for the whole thing and the Y. I'm going to be maximizing the area, so I'm going to call this X and I'm going to call this Y, so that the area is a nice easy formula, X times Y. Now I can't do this yet, they're my dependent, but I got 2 independent variables, so I want to look for another relationship, and it said 500 meters of fencing. So I'm going to have X plus X plus X plus Y plus Y. So I'm going to have 3X plus 2Y meters of fencing is the 500 meters. So to replace either the X or Y, I'm going to have to solve for either the X or Y. I'll solve for Y. So I'm going to have 500 minus 3X divided by 2 will be Y. Subtract the 3X, divide by 2, which is 250 minus 1.5X. So this would become X times Y. And if I distribute that, I get so the derivative, which I'm going to have to set the equal to 0 to maximize the area, will be 250 minus 3X. And so if I set that equal to 0, I get X equals 250 divided by 3, which is 83 1/3 meters. So that's that length, and then I just got to find Y, and Y is 250 minus 1.5 times X. So 250 minus 1.5 times my last answer, and that's 125. I got that by putting this in for the X and solving for Y. And there's my dimensions. All right. We're into Hopital's rule, which was in section 2.8. As X goes to 1, let's see, this would be 1 minus cosine of pi times 1, which is pi. Cosine of pi is negative 1. So 1 minus a minus 1 is 2. So this would be 2, and this would be 0. So the Hopital's rule doesn't apply here. So you can't do that one with the Hopital's rule. And then find the limit. So can we find the limit of this? Well, if this is going to going to 2, 2 divided by something really small will go to infinity. So the limit would be infinity, which is really not a limit. Okay, now this one. If we go to infinity, ln curve goes on up to infinity. So this would go to infinity, and 2 times infinity would be infinity. So they both go to infinity, and for Hopital's rule to apply, they either have to go both to infinity or both to 0. So we now can do Hopital's rule, which says take the derivative of the numerator, and derivative of ln x is 1 over x. Oh, and we got to do the limit still of as x approaches infinity. And the derivative of 2x is just 2. And so that's 2 over 1. If I vert and multiply, this is the limit as x approaches infinity of 1 over 2x. And if x goes to infinity, this will go to 0. So it does apply here. And our limit is 0. Back page. A spherical balloon is inflated such that the radius, so dr dt, is increasing at 1 centimeter per second. I knew it was dr dt because it's centimeters and seconds. What is the rate of change of the surface area? Well, there's the volume. We don't really care about that in this problem right now. All we need is the surface area, which is 4 pi r squared. So if I take the derivative with respect to time, because I'm doing related rates here, so this would be dA dt, not with respect to r. So here I'm going to take the derivative of this, and so my variables are, so it's going to be 2 times 4 pi, 8 pi r to the 1. But since the variables are, and I want to do it with respect to t, I have to take the derivative of the inside chain rule. So it's times dr dt. And dr dt is 1 centimeter per second. So I've got 8 pi. And we're supposed to do this when the radius is 7 centimeters. 7 centimeters times the rate of change is 1 centimeter per second. And so I get centimeters squared per second, which would be a rate of change of surface area. Area is centimeters per second. And it'll be, let's see, 1 times 7 times 8 is 56 pi centimeters per second. And finally, number 10. So we have a fighter jet flying at 800 miles an hour at an altitude of 5 miles. So if this is the ground level, up at 5 miles high, this fighter jet's flying overhead at 800 miles per hour. And it's headed, I'm going to make it going that way, and it says when it reaches 13 miles away from the observer, so the observer's down here, looking up here at this jet flying at 800 miles an hour, 5 miles high, the angle of elevation. So that's from this viewpoint off of the ground. But you can see that if this is flying level and this is the ground, that would be the same as this angle. And what is the rate? The angle is changing. So these both angles will change at the same. As you go further, the angle will get smaller here and here. So we want to know how fast it's changing. So we have to get an equation of the angle related to this jet flying here. So I'm going to call this distance x, and then we're going to let x be 13 at some point, but we don't want to put 13 in yet. So the relationship of this angle and these sides would be the tangent of the angle is 5 over x. Or I could write cotangent of the angle is x over 5. Either way. Now this one might be a little bit easier to work with because x is in the numerator. This is the same as 1/5 x. So if I take the derivative with respect to time of this one, I get negative cosecant squared of theta times d theta dt equals, and the derivative of this would be 1/5 times dx dt. So there's the plane is traveling at 800 miles an hour, so that's a change in this length. So dx dt is the 800 miles per hour times a fifth. So 800 divided by 5 is 160, and that would be miles per hour. And this cosecant of theta will be, so I'm going to look at this triangle and figure out what the cosecant of theta is. And the cosecant is 1 over the sine. The sine would be 5 over this, 5 over this side, and this side will be the square root of 5 squared, 5 squared plus x squared. And so the cosecant is 1 over the sine, so it would be square root of 5 squared plus x squared over 5, and we've got a minus, and that's got to be, the cosecant part's got to be squared, not the negative. So I'm going to get this times d theta dt, which is what I'm trying to find, how fast the angle is changing. And I'm supposed to do this when x is 13. So I'm going to put 13 in here. So I'm going to get 25 plus 169 square root. That's 13 squared. And I'm going to take the square root of that and then divide it by 5 and then square it. And I get this, which is going to be negative, so I got to take 160 divided by this. So 60 divided by the negative of my answer, and I got negative 20.62, and that will be the change in the angle, so this would be radians per hour. Okay?